Okay, we want to find out what the angular momentum is going to be about a point right here. And this distance is 6 north, right? Okay, so does that make sense? Make sure you understand what this says. 2 kilogram particle moves directly eastward at a constant speed of 4.5 meters a second along an east-west line. What is its angular momentum, including direction, about a point that lies 6 meters north of that line? Let's say, included about a point. What's that? No, they're basically saying, based upon that point, what would be the angular momentum if it's going around like in a circle? So right there where it's tangent, yes.
The particles can moving like in a straight line.
It's moving along a straight line, that's right.
It can still have angular momentum.
It can still hang angular momentum about that point. And where it comes into, where you use that a lot is like an object that's, say, a bar is hanging and some particle coming along and hits it right at that point. Well, it has initial angular momentum, and what we'll find out is you get conservation. The final momentum will be the same thing as the initial momentum. So after it hits it, you can find out what the rotation of this rod will be as a result of the conservation of angular momentum, which we'll talk about in just a second. But yes, about that point, you can say it has angular momentum. Yes?
Shouldn't your velocity be 4.5?
Oh, thank you. Yeah. Okay, so now we can do this two ways again. L is going to equal to the cross product of R cross product mv, right, which is linear momentum. So when I do that, I say L is equal to, if you do it with the cross product, this would be -6 cross product, and you can make it j hat if you want to. I wouldn't necessarily do that. Times 2 times 4.5 times I hat, right? So that's 9. That gives me what? Equal to 54. Now, that's negative, but now, right when you do the cross product of j cross I, you get a negative k hat, right? Yes?
Why is it negative?
Because if you do right-hand rule, right, this is negative here because I'm going down negative, right?
What is it relative to?
What's that?
What is it relative to?
Everything's relative to this point. Here's my 0, 0 axis right here. This is here and here. So if I take everything based upon that, is from here I go down -6. That's -6 j hat. This, in relationship to this, is going 2 times 4.5 I hat. So, and I do that if I do j cross I, right? If I do j cross I hat, don't I get a negative times negative k hat? Which in this case is going to give me 54 kilograms times meters squared over seconds. Okay, I'm just saying, what I would do would be, instead of worrying about doing this with a cross product, think about it in regards to this. What direction is this object going? If it's going in a circle, you're going to go this direction. So that's going to be, when we've established that as positive, right? If it goes counterclockwise. No, about this point here, right? About that point here, this object is trying to go. If this is the axis, it's tangent, so it would be going in an arc. If this was like a string or something, it'd be going in an arc. So it's going positive z, according to the right-hand rule.
How if it's going east, how is it? I thought the particle was just going straight.
It is, but I'm just saying, in relationship to this point here, what is this angular momentum? Angular momentum would be, in regard to this point, is going to be the cross product of this times mass times velocity. So if it was going this way and I had this, it would be like it would wanted to go right into a circle. You're just trying to establish what would be the angular momentum at that point. It would be like going clockwise or counterclockwise, which is positive. Right, when we did torque and we established anything that goes counterclockwise is positive. Yes, true. Okay. So here you would give it positive angular momentum of 54 kilograms times meters squared per second. Yes.
So basically, from just what you said, angular momentum and torque curve, you treat them as the same when it comes to establishing direction.
Yes.
And how are they related, like, other than that?
They're not related. I mean,
Yeah.
torque is equal to inertia times angular momentum, right? I mean, angular acceleration.
Yeah.
Right? You agree with that? That's the only relationship you can say they have. If you apply a torque to a system, you can change the angular momentum of the system. But that's the only relationship they have. And we'll talk about that in just a second. Other questions? Yes.
And with the direction you can already tell what sign you're going to use by just eyeballing the...
Yeah, I would. I wouldn't necessarily go through and do all the cross product.
Yeah, you don't need J cross product I.
No, you can, and you'll get the same answer.
But it's just not necessary.
I don't think it's necessary. Right? If I'm going to go, if it went back the other way, when you say, well, it's going to be negative 54. Okay? Now, I won't do the other axes, but it would work exactly the same way. What's angular momentum including about a point that lies 6 meters south? If it's 6 meters south, it would be exactly the same value, but it'd be negative, right? If I took this point and moved it down here, now it would be wanting to go clockwise, correct? So it would have negative angular momentum.
Part C, how's that? Would it just be not?
What is the angular momentum about a point that lies 6 meters directly east of the particle?
Does it not have it?
It would not have angular momentum. Yes, Howard?
What is angular? Is it like the tendency for a particle to
Remain in motion, or in circular motion?
circular motion?
Yes. Same way, what is momentum of a particle? It wants to continue with.
But in this case, it's not going in a circle.
No, it would not. It's not. But I'm just saying, in relationship to that, you would say it has angular momentum, and you're absolutely right. It's not going to go in a circle. But if it's going to collide with something that is pinned, then you have to work it this way to find out what the angular momentum of the object is after it's, say, hit or whatever. Yes.
So for part C, the angular momentum would be 0? Or
0. Yeah. Yeah. Because this in this way, the mass and the velocity and r would be in the same direction. Now, everybody understands, again, and I won't work this unless you want me to, that you could also work it this way, which I wouldn't necessarily do it, and you get exactly the same answer. I mean, do I need to do this again, or can we accept that? Okay. All right, let's look at the person here. Find the angular momentum. Can you guys do this one? Find the angular momentum. It's a 0.3 kilogram frisbee, uniform disk, a radius 7.5 centimeters that's spinning with an angular speed of 1.15 radians per second. So here I just have a frisbee, and it's spinning around its own axis like that. And it has an angular, and again, you don't know what direction, it doesn't say. So you can make it either way. I mean, does everybody understand this? This would be really easy, right? Wouldn't you just do L is equal to the moment inertia times angular velocity? So when you just have 1/2 times 0.13 times 0.075 squared times 1.15. Does that make sense? That's it. You're done. I mean, that's all it would be. Let me ask you a question. What would happen if I asked you what would the angular momentum be of a point here, and you're rotating around a point right there? and I told you this distance was 5 centimeters. Parallel axis there. So if I gave you that point there, would you not have to do I? The only difference would be I would equal to 1/2 times 0.13 times 0.075 squared plus its mass 0.13 times 0.05 squared. Right? That'd be your new angular momentum about that point there, but you'd use the same angular velocity. Does that make sense? Yeah.
So the parallel axis theorem can be when you have another point doesn't matter if it's inside or outside your original.
Doesn't matter. Yeah, doesn't matter. Okay, and I won't work this unless you want me to, because I want to get through all this lecture. This one I got a 95-kilogram person running around at speed around a circular track. Wouldn't that just be mass times velocity times radius? Agree with that? Okay. How would you do this? How would you do a problem like this? You got a kid, 21.2 kilogram child, running with a speed of 4.1 meters a second, leaps toward the rim of a merry-go-round at radius 2 meters. What is the child's angular momentum, L, with respect to the center merry-go-round? Now, does everybody understand you cannot just do this? L is equal to 21.2 times 4.10 times 2. That's incorrect. Does everybody understand why? Yes.
Because he's not perpendicular to the radius.
Yes, that's exactly right. So in this case, when you basically do this, isn't L just going to equal to 21.2 times 4.10 times the cosine of, I'm going to make it 45. Everybody, I hope you see where I'm doing that. Cosine of 45 times 2. That would be his angular momentum. And again, I would make that positive because when he's wanting to go this way around that point. Does everybody in the class see where I got? Hope you see where I got that. Yes.
Wait, wouldn't that be the sine of 45? Because you have 135 degrees. And then
Well, I'm just saying I'm making this angle 45 degrees. So if I take this velocity times the sine, I get the perpendicular one.
yeah. Which is
Sine. I'm sorry, you're right. Yeah, sorry. Well, okay, I know what I did. Here's what I was thinking about. I was going to do it like this. Same thing. I was looking at this angle here. This angle here is 45. Yeah, in this case, it doesn't matter. But you see what I'm saying? When I looked at it, I was thinking this angle was 45.
Yeah, I was thinking the angle between the.
In this case, it doesn't matter. Okay. Let's change it then. If, say, something was like this, and let's say he's going this way, and this angle is 155. Okay, you got your choice. You could take 155 minus 90, give you this angle, and then do the cosine, right? Or you could take 180 minus 155 and then do the sine. You get exactly the same thing. Did that answer your question? Huh? Okay. Yes.
Yeah, I looked at it at the angle, like, just right above the vector z, and between, below the, like, the right a little bit.
What do you want to do?
I looked at the angle underneath where your cursor is right now.
Yeah.
That's where I thought it would be the sine of 45. Right? That's the angle I used.
Oh, I see what you did. Okay, gotcha.
Yeah.
Okay. Yeah.
I mean, is that a-
Yeah, no, you can do that. No, you can do that. It's fine. Yeah. Okay, so that one's pretty easy. Some of these I'm not going to work unless you need me to work them. Yeah. Okay. Again, some of these problems I'm not going to work. I want to discuss it more than work it. Like this one, is what is the angular momentum of the Earth as it rotates on its axis? So all you would have to do on this one would be find out what omega is based upon the 24 hours, correct? This rotates 24 hours in one day. Find out what that would be. Treat this as a sphere, solid sphere, and just go back and use L is equal to I times angular velocity. And that's all you would do with a problem like that. But again, you have to treat I as a solid sphere. And then angular velocity is going to be based upon the time, right? 24 based on 24 hours. Get it down into radians per second. And that will tell you what your angular momentum is going to be. All right. Another problem, a similar problem. Now this problem is a very interesting problem here. What is the angular momentum of the Earth as it orbits the Sun? So the first part would be pretty easy, right? You could say, well, I would be equal to, I won't do I, we'll do L here. We could say L is going to equal to the mass of the Earth, times the velocity of the center of mass, just times the radius, correct? Did I agree with that? Now that would only apply if the Earth is not spinning. Would you guys agree with that? That's so far okay? But now what happens is the Earth is also spinning around its axis. So what you would end up doing is you would have to add I times omega, and the I would be the moment inertia of the Earth, and omega would be the angular velocity of the Earth. Does everybody see what I'm doing with this one? But note this, and remember these are vector quantities. If this one is spinning this way and the Earth is going this way, you add them. But for example, if the Earth was spinning the opposite direction, like that, but you're moving this way here, you would subtract it. Yes?
That R there in your equation, is that the radius from the Earth to the Sun?
This is the radius from the Earth to the Sun. Yes?
Does it matter that it's at the angle that it is? It's at the Earth tilted on the axis.
It's tilted, and then the no, it would. Let me think about that. If it's tilted, it would make a difference. So this would have to be, and this is what this picture is really trying to say. They are the same axis, but yeah, it would make a difference. I don't think you're not going to get a problem like that in AP Physics. You might get an engine.
The whole system is tilted.
Yes.
The sun is below.
What they're trying, on this problem, they would not have made it that complicated. They're trying to say that these two axes are parallel, because if they're not, you're absolutely right. You'd have to use trig to get which one is parallel to that axis. Okay, what's interesting about this means, when you think about this in a logical standpoint, if you had, I'll make it here like this. If you have something that's spinning around like this, and now you have a mass out here that's also spinning around, if the mass is spinning this way, it's going to take a lot more torque to stop it, right, than if it was spinning this way. So if this object's spinning this way, but it's also moving this way, it's going to take less torque to stop the object than if they're both basically going the same direction. Yes?
Can you explain that more, please? Because I don't quite understand saying that less torque if they're both rotating in the same direction or opposite?
Okay, if they're both spinning, if this is spinning this way, this is going this way here. Okay, would you agree that it has greater angular? It has a large angular momentum versus if this one's going this way and this one's going this way. Do you accept that?
Because if one's going the other way, then it's attractive.
Yes.
Yeah.
Yes. So if it has less angular momentum, it needs less torque to stop it. Basically, it means it works the same way with linear. If a big truck has a large amount of linear momentum, it's going to be hard to stop it compared to, say, Volkswagen that has like a lot less mass, right?
But the same velocity.
But the same velocity, yes.
Yeah.
So it's the same type concept. If you have greater angular momentum, it's going to take greater torque to stop it.
Yeah.
If it has lesser angular momentum, it's going to take less torque to stop it. So you're going to see a UT problem when you get to I think it's the coin. I don't know if anyone's done the coin yet. You have a spinning coin, and it's spinning, but it's also going around something like this. Make sure you subtract the angular momentums on that because they're going opposite directions on the Webb-assigned problem. All right, so everybody feel fairly good about angular momentum basically right now? Okay, I'm going to go over to the second part of this lecture, and then I'll get you guys going. This is going to take a little bit of time. And the problem I was mentioned too was this point here was the coin. I won't work the problem. Just work through this problem. This is one of the, again, Webb-assigned problems. You're going to have a coin. Now, it gives you the moment of inertia here, right? What you're going to do on the coin is let L approach 0 because the coin is very, very thin. So when you do your moment of inertia, just use I is equal to 1/4 mr squared because you have a coin that's spinning basically like this. You have a coin that's spinning like this. I'm facing you, right? It's like this, though. So when you do the moment of inertia, just do 1/4 mr squared because what they're doing, they're letting this thickness basically approach 0. It's very thin compared to its diameter. Is that acceptable? All right, so you won't have any problem with A, B, and C. And now note, if you have something like a coin, let's take an object here. If you have an object here and it's spinning like this, it doesn't matter whether I'm right here or here or here or here or here. Its angular momentum is exactly the same in respect to those points. As long as but if I do something like this, then do it with vector. If I do something like this, the whole ballpark changes. Because now I have to consider this velocity times this mass multiplied by that radius, and it has to be a cross product perpendicular to one another. But if this does not have velocity, then it doesn't matter where I move, the angular momentum will be the same. Now part D says, and they did a lousy job writing this, but I'm going to tell you right now that when you do this problem, they are going opposite directions. And the wording is pretty crappy, but when you get to this problem and you can't get the right answer, just subtract the two momentums and you'll get it right. Okay. All right, changing angular momentum. As mentioned here, that the change in angular momentum over the change in time is going to equal to what is torque. So basically, torque is going to equal to change in angular momentum over change in time. Now, most of the problems you're going to see, there's not really going to be torque involved. And torque has to be external type torque. It has to be like a gravitation. Something has to be causing torque. So I don't want you, it's the same thing when two particles, like you got something hanging here and something comes hitting it. As a system, there's no torque involved. But if it's hit and then go on, you could say, yes, there's torque applied to this object. But when you start doing these work these problems, when both the particle that's hitting it and the bar is part of the system, there's not going to be any torque involved. Same way as when you guys did collisions, right? When they did collisions, then there was no force really involved, right? That there was conservation of momentum when you did collision. Remember that when we did elastic, inelastic, always conservation of momentum. Works the same way with angular momentum too. Whatever the initial momentum will be, the final momentum will be the same thing unless there's some external torque that's being applied. Okay? All right.
In that situation, that wouldn't gravity pull the bar back down?
Gravity, yes. If gravity is involved, it is going to be an external torque, yes. And so, yeah, angular momentum will change in that case, absolutely. So, yeah, if I had a bar, like you're saying here, its initial angular momentum would be 0, right? But now if I let it go, a torque's been applied because gravity's pulled down, then there is a change in angular momentum in that case because gravity acts as an external torque. Something's called an external torque. All right, let me get my notes together and we'll start working through some of these problems. Let's see here. All right. Let's see. First problem right here. So on this problem here, again, we can say that delta L, change in L, or change in angular momentum over change in time, is equal to torque. So here you got a windmill experiencing a constant torque of 255 Newton meters. So 255 is equal to delta L over delta T. But now it says its angular momentum after 2 seconds. All I have to do on this one, take out that, put 2 in. So what is angular momentum after 2 seconds? Then they're going to be delta L is going to equal to 255 times 2. What is that, 510? And that would be kilograms times meter squared over second. That one's really, really easy. Okay. So initially it was at rest, so my initial one would equal to 0. My final, in this case, would equal to 510 kilograms meter squared over seconds. Yes?
So what the units for angular momentum, could it also be newtons?
Yeah, I mean, it's the same thing. If you went through the unit conversions and convert everything, you'd get exactly, you can get back to this. This is normally what you see it as kilograms times meter squared per second.
So Newton is a kilogram times meter or kilogram?
Well, a Newton, okay, I won't do the whole thing, but Newton, in a Newton going to be a kilogram times a meters over second squared. Right? Isn't it? It's going to be mass times acceleration, right?
Yeah. Mm-hmm.
So now if you take, that makes sense? You'll get to that unit if you just do the, you know what I'm saying, if you just do the rest of it. Right? If you multiply, let's say here, let's see, if I multiply by time, let's say meter squared, let's say Newton, sorry, all right, we got Newton meters, okay. So you multiply Newton meters. So Newton meters, 1 Newton meter is equal to meter squared. You agree with that?
Yeah.
Make sure you agree with that. Okay. Newton meters is kilograms times meter squared times seconds, right? Mm-hmm. Now if I multiply that by seconds, what happens?
Yep.
You get exactly the same thing.
Mm-hmm.
But this is traditionally the way it's the typical unit.
Yeah.
Okay.
So Newton meter would just multiply the m by the n limit, distribute the.
Yeah. Yes.
Kilogram.
Yes. All right. This is an interesting problem here. You have an individual. He's spinning. He's spinning at 374 radians per second. He has a moment inertia of 5.33 kilograms meters squared. He's going to pull in these little dumbbells, and now his moment inertia is going to change. Okay? Now, there's no torque involved here. So, what's interesting here is you'll find out that L initial must be L final. Okay? And this is what makes an ice skater, when they bring their arms in, they can spin really, really fast compared to their arms out. That's why that's all they do. All they're doing is changing their inertia. So we'll set this problem up. L initial would equal to moment inertia 5.33 times 3.74. That would be my initial. My final would equal to 1.60 times omega final. Okay? So when I just do, someone can run this number, please. 5.33 times 3.74 divided by 1.60. Doesn't that give me my final one? Let me see if I got my notes on this too, so I could save you guys a little time. Yeah, actually I do. And I got 12.46. Make sense? So by changing the moment inertia, you can spin faster. Okay. I'll work a couple more problems and see which one I want to work to. Actually, I'll let you guys. Can you guys do this one? This is a good problem here. That way, I'll work this one. You guys work this one. I'll work a couple more and we'll be done. Here you have a uniform 130 kilogram rod with a length of 44 centimeters. It rotates in a horizontal plane about a fixed vertical frictional pin through the center. Two small 22 kilogram beads are mounted on the rod such that they are able to slide without friction along its length. Initially, the beads are held by catches at 10 centimeters on each side, and now you're going to release it. And when you do, the beads will slide out. So what I want you to do on this one is tell me what the final angular velocity is going to be once you release it. So the picture would look kind of like this. You're spinning around a point right here. You have a bead here. So that's what it's going to look like initially. And then it's spinning like this. Again, I'm going to let you guys work it. It's spinning, I don't care which direction you want to go, just be consistent. So it's spinning at 24 radians per second. Now, what's going to happen final? These beads have slid all the way out to here.
Could that actually happen?
I mean, you could design something that could do that, sure.
I feel like the beads would just fall off.
Well, if they had like little grooves, they'd have to have grooves in, yeah. Yeah. Can you guys figure out what would be my new angular velocity?
Which way is it rotated?
I made it clockwise. You made counterclockwise. It doesn't matter. I don't think it says, does it?
But it's spinning horizontally, right?
Yeah, but I'm looking down on it. I'm looking down on it.
Looking down.
Yeah.
When you slide to the edges.
What's that?
Understanding makes sense, but why do they go to the edges?
Well, okay. Why would they get? Well, I mean, they have catches here. Okay, and the question is your question why if they did not have catches, why would it go to the end?
Yeah.
Because they want to go as something spins. Like for example, if you go around a corner in a car,
Yeah.
and you have something on the dashboard and it slides along the dashboard. Why does it slide? It doesn't slide. It doesn't slide. It does.
The car moves under it?
Yeah, what happens is that it's wanting to go straight. So it's going straight and the car's going like this.
Okay.
So it slides down.
That makes sense. So,
That make sense to you or not?
I guess it wants to go straight. But
It wants to go straight, yes.
the rod kind of slides out.
Yes. Yes.
Because it's not nothing's like pushing.
No, there's no, I don't want you to think there's some magical force that pushes these beads out to the end. It's not. They're wanting to go straight. You'd have to do mr squared. The inertia would change.
Like,
Yes. Yes.
The rod of the rod has mass too. What's this? What's the?
can you tell us another inertia equations?
Yeah, I'll give you all the inertia equations on the test. Yes.
Solid cylinder through diameter, or
I'll give you the one for this one too, here real quick.
It's 1/4. Is it 1/4 ml squared plus 1/12 ml?
Well, I would do 1/12 ml squared, or r squared. Really makes no difference. Yeah. So a rod about its center, the moment inertia of the rod.
What's the difference between a thin rod and a solid cylinder?
Wait a second here. ml squared. What's that now?
What is the difference between the idea of like a solid cylinder and a thin rod?
Well, I think what they're trying to say, there's a large relationship between the r and the length in this case.
So
And but you're spinning. If you do a solid cylinder, you're going around the.
there's another one that's like. Solid
Oh, you're talking about the 1/4 mr squared?
Yeah, plus 1/12 ml squared.
Yeah.
It doesn't give us a radius, does it?
Yeah. So what you would only use that one, and they should tell you when to use these. But that would be where you have a large R value compared to the L value.
In this case,
You don't. So if it says thin rod, you'd have to use 1/12 ml squared. And again, if you're getting into, like, if you're working in the engineering business where you're designing things like this, they're going to have books that tell you exactly, what inertias to use based upon R's and L's. But for a physics class, they just said, oh, it's a thin rod. Now, this is the value I want you guys to be able to get. I got this, and tell me if anyone can come up with that one.
What did you get for your initial?
0.060896 or something like that.
for the V's, do you do other I times omega, or do you do n r times
Okay, well, if I'm going to do, first thing, do the inertia, right? So you're going to use this equation here, and then you're going to have to do mass times radius squared, and you're going to have two of those, right? So you're saying you're going to add that to that inertia. That's going to give you a total moment inertia. Here's what you should get. For total moment inertia, tell me if you guys get this. Total, I got 0.002537. You should get something close to that. That's your initial inertia. And I did not calculate final. I did it with the answer, but. You multiply that by your 24 radians per second. That establishes your initial angular momentum, which means your final angular momentum must be the same. Howard?
Are the beads, are they particles? Are they spheres?
They got to be particles. But they're not giving you, they'd have to give, you bring up a very good point. They'd have to give you a radius if they want you to treat them as spheres, because otherwise you couldn't do it. Yes?
I don't quite understand how you got the total moment of inertia initially. How you add an mr squared?
Okay.
How exactly did you add that? Did you-
So you would have done, you treat these as point masses.
Yeah.
Okay, so it's going to be, they're going to do 22 divided by 1,000, okay, times what are 0.10 squared. That would give you the moment inertia of one of these about this point here. You got two of those, so you take that value and multiply that by 2. Then just use the equation 1/12 times the total mass of this rod times this length squared. Add those two together and you should get a value like that.
Yeah, I've got it.
Okay, good.
I see what I did wrong. I used 0.22 kilograms instead of 0.02.
Okay.
Yeah.
Is everyone in the class at this point right now? I mean, that you got this or not? Okay, take your time. And I'm be honest, I'm probably going to give you one test problem similar to this. I mean, something like this. This is pretty doggone easy. But what's that now? You did? Okay, so you got that for inertia.
Yeah.
Okay, so
Oh, I think I'm correct with that. Yeah, never mind, I got it.
you got it?
Wait.
Yeah.
Oh, never mind. It's like that
Let me see what the next problem is. Okay. Are we all good yet or not? Not yet.
Would you get for the final moment of inertia?
I didn't calculate. I built it into the problem. If you get this value here, you know you got it right. If you got really close, you're fine. I mean,
It was like 0.17.
you got 14.17. Is that?
Yeah.
Okay, that's, yeah. I mean, you must be a rounding issue or something.
Can you set up final, whatever, like,
Okay. Yeah, I can do that for you. So, first question I'm going to ask you, did you get, let's say, let me get this, L initial, make sure you got this first. I got 0.060896. Did you get that for initial angular momentum? Or do you want me to work that also? Okay. Okay, but you agree with, do you agree with this? Okay, so all you're going to do then to do that, then the initial angular momentum is going to be I times omega, right? So we put in 0.002537 times the 24 radians per second. Does that make sense there? And that should give you, I think, a value like that, does it not? Okay. So then you know Li is going to equal to 0.0608996 times kilograms times meters squared per second, right? So now, doesn't that mean that L final must equal to Li? There's no torque. There's no external torque being applied to this system. You accept that? Okay. So then you're going to do this. 0.060896 must equal to my moment inertia, which we'll calculate. And you got to go back and do 1/12 times the mass, which was 130 over 1,000, times its length, and it was 44. And then you're going to do this, plus, I got two of these guys, so I'll put 2 times the mass of the beads, and the mass of the beads were 22 grams, 22 over 1,000, and now they've moved to the end, right? So are they going to be 0.22 squared? That should give you the total moment inertia. And then just set that equal to final, and you solve. Okay, I'm going to work 2 more problems and we're done. After you get this. You okay with that?
all of that is multiplied by omega final.
That's omega final, yes. Because, again, just this. Moment inertia times omega. Okay? All right. skip ahead here. This problem here, I did a video on it, so I'm not going to work it. It's on the calendar. Okay, this is one that has torque involved because gravity is involved here. This is the problem this problem, I promise you, is going to be on the test. This is an awesome problem.
Did you post the video of that one or not?
No, I'm not going to do a video of this one. All right. So please watch this. It's a cool problem. You got a small piece of putty, a mass 41 grams, negligible size. So we don't have to worry. When we're going to do the moment inertia, we're only going to do mr squared because it says negligible size. Has a speed of 2.4 meters a second. It makes a collision with a rod that is 7 centimeters, a mass of 88 grams, such that putty hits the very end of the rod. The putty sticks, spins around. Okay, now what's cool about this problem, I love this problem, is that this object is not, it doesn't have a rod through it. So what would happen with an object that's hit, it's always going to want to spin around its center of mass, right? Like this. If it's hit like this, it's going to want to do this. But what do you think is going to happen if the putty slides, small putty slides in and sticks? What's going to happen to the center of mass? It's still going to rotate, right? What's that? Center of mass is going to shift up. So now instead of rotating around the middle of this, it's going to be rotating about a point that's slightly above the middle of this. Because that's the new center of mass. That's what I love about this problem. Okay, so what we would do here, we could set this up. We need to find out first where's the center of mass. So we're going to base the whole problem upon what happens right at impact, right here. Okay, so we'll do the calculation for center of mass. I'll draw a picture. And I think, honestly, I did a video similar to this, maybe, but I don't think this. I think the only difference was, if I remember right, the problem I did on the video, the center of mass could not shift, I believe. All right, see how good I can do this. We'll get the little putty. Oops, that's not very good. Okay, it's stuck on there. Okay. So now let's do our calculation. And it says it's stuck on the ends. Let me slide it up just slightly. Just like that. Okay, the length of this is 7 centimeters, right? So again, it doesn't matter whether I change this to meters or 7 centimeters right now, right? To do center of mass. So I'm going to let this be my x-axis. To do that, can I not say that x bar is going to be equal to the mass of the rod, and the mass of the rod is 88 grams, right? So can I not say 88 times 3.5 plus 41? Yeah. So there's right here are the two center masses. I got one right here and one right here for right now. So I got 88 times 3.5. I come up and the putty weighs 41 times 7. I divide it by the summation of the masses. Can someone please run that number and tell me what you get? What's that now? Not to do, I mean, you're going to have to when you do like angular momentum and things like that. Not to just find center mass makes no difference, because they would cancel out anyway. Someone can give me that value. I'd like to know what that is. 4.6. 6 what? 6.1. Okay, so 4.61. So that means the center mass has shifted up from here to here, 1.11, right? Yes, gentlemen.
So when you take the center of mass in respect to the axis, you do it parallel or perpendicular? I thought we were doing it parallel. So you have
No, I mean you're doing all your distances, right? I'm trying to find out what is the what is the distance from here to here. So I have to take all vertical distances.
so there's no horizontal distance.
Yeah, I see what you're. I got your point. I should have called that y bar. You're right. No, I apologize. Should have called it y bar.
So your center of mass would be, your initial one would be in red, right?
Yeah, this is the red is the center mass of just this piece here. This red is center mass of the putty. So the new center mass is the blue for the system.
And we're treating the putty as a single point.
Yeah.
So how did we get 1.11 this
It's 4.61 from here, right? But now, based upon this value here, this is what it was originally for the rod, right? So 4.61, wouldn't it be 3.5 from here to here? So I'm just saying, it doesn't matter. I mean, it's just so you know where it is. I just said 1.11 from this point.
So the original center of mass is the center of the rod.
Yes. So now, what is this distance here going to be? Because this is critical. What's this distance right here? Someone give me that. And it's going to be 3.5 minus 1.11.
2.39 centimeters.
What is it?
2.39.
39 centimeters. Okay.
Is that the distance that you need?
Yeah, that's the distance we're going to do. Because
If we just set the where the putty is as a reference point.
you could have very well done that. Very good point. Yes. Yes, you're absolutely right. You could have just set that as your reference point, absolutely, with a simpler problem. Yep. Okay, so now, would everybody agree, once that hits, this object's going to want to rotate. It's going to rotate around this point right here. Does that seem logical? All right. So let's work the problem and find out what the initial angular momentum of this problem is. So my initial angular momentum, right when that putty strikes, isn't it going to be m times v times r, or r cross product mv? Either one. It's the same thing. And again, I'm going to let anything that goes this way be negative. So when I do that, L initial must be the mass of the putty, which we said was, being brain dead here, sorry, 41. So 41 divided by 1,000 times its velocity, which is 2.4, times r, which is 2.39. Can someone run that number and tell me what you get? What'd you get now? Yes. So change that value. Let's see what I got here. Hold on a second. What do I have here? I have mass times velocity times r, and change that to centimeters. So divide that by 100. Did you get like 0.00235 or something like that?
Yes.
Does that make sense there? So that's going to be in kilograms times meters squared over r. I mean, over seconds. Everybody go with that. So now, can we not go back? There's no torque being applied here. L final must equal to 0.002358 kilograms meters squared per second. Okay? Now, can I not say this? LF must equal to I times omega. And that's my omega final. Now maybe the hard part is this guy, right? That's the hard part. This is this is you're just going to get by taking this value here and dividing by I. Then you're going to get final. Let's talk about how to do a moment inertia with something like this, because you're going to use a parallel axis theorem quite a bit on this one. So my new system, I come back and I'm going to use a rod, and a thin rod that's rotating around. What did we say that was? 1/12 ml squared, right? I'll get that piece of paper later. Okay. So when I go back, I'll do 1/12 times the mass, which is 88. I divide it by 1,000. I take its length. Its total length is 7. Okay, so let me ask you a question. Am I done? Is that the moment inertia of the rod? It's not, right? That's the only moment inertia of the rod about its own centroid. So now I have to go back and do this, plus 88 over 1,000 times 1.11 over 100 squared. So that's the moment inertia about the rod using the parallel axis theorem. Does that make sense, everybody? And then, am I done or not? Still got to do putty. Then you got to do plus mr squared. The mass of the putty is 41. So I take 41, I divide it by 1,000. We multiply it by the distance, which was 2.39 over 100. Square that. And let's see if I even have it. Hey, I do have it. I got. Let me put this on here for Rebecca. This is the putty.
This is the momentum of the rod, PA.
What's that now? I just said parallel axis theorem. Okay. So the total inertia of the new system is equal to, I got 7.02 times 10 to the minus 5 kilograms times meters squared over second. PA. What's that? I just said parallel axis theorem. Can someone confirm that or close to it?
Wait, is it angular momentum?
What's that now? Okay. I may make this the last problem today, so the other one I can work tomorrow in class too. Because if we finish this one, this will put you exactly the same place AM1 was. Okay, so now it's really a piece of cake, and then I come back here, I take this value here, let's grab it. And the reason I like this problem has shown up in the AP exam before as a free response question.
So this exact same problem.
Well, I mean, it's a very similar problem, yeah.
We asked them for the exact same things at least.
Yeah.
Same items. So that's what that is.
And I got a mega final. Yeah, it's 33.5.
Can we go back up to the equation?
Yeah, just a second here. That good enough?
Yeah.
particular conservation
Yeah. I'm glad. Yeah. That's what I'm gonna do tomorrow in class. Yeah.
But is it changed at all because there's now an angular component?
Mm-mm.
Okay, so it's just MV.
Yeah. Ben brought up a good point. He said, could you find out what the velocity is going to be of this system? Because it's not like spinning, it's moving. So all I'd have to do that would be, I would say, P being the initial linear momentum. Wouldn't it just be? It would just be mv, right? It'd be the mass of the putty times the velocity of the putty is equal to the mass of the putty and plus the rod would equal to the velocity of the putty plus the rod. And you could find out, and that's a good question. I'll probably ask you that in the test actually. What is the new velocity of this system? So not only they're spinning, they're also moving this way. So the conservation of linear momentum applies also, because it's just a standard collision. I mean, I think it's cool as crap, don't you? I mean, I think it's neat. Questions, comments? What do you think? Not too bad? Okay, I'll show you. This is the problem I work tomorrow, and I'll answer your question. The problem I'm going to work tomorrow in class is kind of like what you just said here, but now they no longer stick. It's a perfectly elastic collision, but they don't stick. This is a cool problem because you end up with 3 equations, 3 unknowns. You get the conservation of angular momentum, you get the conservation of linear momentum, and you get the conservation of kinetic energy. And that's when I work tomorrow in class, and then we'll get you going on. Some problems related to test. But again, any of these problems are fair games on AP exam. The free response questions will be more like these type of problems, and they don't really expect you to get them, but they expect you to at least show some work that you can get some of the points. I mean, obviously, some people are going to get them.
Do you expect us to get them?
Yeah, I think everyone in the class capable of getting every problem. I think you're capable of getting every problem on the test right, personally, but I don't think that's going to happen, but I think you have the capability to. Because you will have seen basically every type of problem they could throw at you. They're going to be formatted differently. But you shouldn't see any problem on there that's like, oh, I've never seen a problem like this ever in my life. All right, you guys want to just take a 10-minute break and then come back and you work on homework, and I'll help you with anything you want help on 10-1. Yeah. Yeah, I can do it right now. Sure. Yeah. Did you send me a request or not? You can't? Okay. Send it to me, or I'd rather do that than open up for about. Yeah, question?
Is it possible that you can print out the previous slide?
Yeah, I can print out for you. Sure. Let me finish this. Let me shut this video off.
The one on the rod and the